Hello, welcome to Unit 1 Kinematics. Today we'll be going over a few concepts and reviewing a few problems from the unit. Let's get started. So remember that our first formula is going to be v final is equal to acceleration times time plus v initial. Acceleration and velocity are both vectors, so pay close attention to their directions. And for instance, in a free fall problem, gravity is going to be negative, right? It's going to be pointing downwards. So that whole term, acceleration times time, is going to be negative. So just keep an eye out for that in case you need to use the direction. And anyways, if you take that formula and you integrate it with respect to time, you're going to get the distance traveled is equal to 1/2 at squared plus v initial times t. Now, remember that in this formula, you can always add a starting position. If the problem gives you start at a certain position that's not 0, then you need to add that to the right side of this equation. Okay. And remember, for most of the free fall problems, if you don't move at an initial velocity, just remember that you can put in 0 for vi, so that whole term becomes 0, and you're left with d is equal to 1/2 gt squared. And remember, the negative and positive signs do apply here, so it could be 1/2 gt squared or negative 1/2 gt squared. It's depending on how you see the positive direction to be. And always remember to convert your units to SI. For instance, meters, seconds, kilograms, and consider vertical and horizontal movements independent of each other. And why is converting to the international system of units so important? Because in the future, when we're looking at forces and we're analyzing those, you're going to be needing to use the SI units, or else you're going to end up with a wrong calculation sometime. So just keep an eye out for that, pay close attention, and let's move on. Now remember that when we're looking at gravity and problems relating to free fall, gravity is always going to be a force field on the planet, meaning it's everywhere and it always acts downward. It's going to be also with an acceleration of 9.8 meters per second squared. So look at these two diagrams here. The one on the left just shows a block falling downwards, right? Just completely vertical motion. It's just directly at the vertical angle. So it's going to be falling directly downwards at 9.8 meters per second squared. Now, if I gave you the right-hand setup with a block on an inclined plane at, say, an angle theta, would you still know which direction the acceleration is going to be going? Well, yeah, because as we've said, gravity always acts downwards. No matter which direction your object is or what angle it's at, it's always going to be pointing downwards with 9.8 meters per second squared. Now, the tricky part comes when the problem asks you to find what, for example, the acceleration going down the ramp, along the ramp, right? That's going to be a little bit different. You're going to be having to look at vector projections, and those are basically when you're decomposing a vector into certain directions, right, to analyze its motion along a certain direction. And in this situation, you're trying to decompose the vertically downwards acceleration into one component that's pointing along the ramp. So along the plane that is inclined at an angle of theta degrees. And so we've done the math for you. It works out to be the acceleration of gravity down a ramp at an angle of theta is equal to 9.8 times the sine of that theta, meters per second squared. And so most problems probably won't ask you to calculate this actual value. They'll just test you to see if, you're going to respond with saying that going along the ramp, it's going down at 9.8. Well, that's not right? Unless the ramp is horizontal, which obviously is going to be 9.8 downwards. Remember that along the ramp is still a different direction than directly downwards. So it's going to be a little less than 9.8 in most cases. So let's take a look at a derivation of a formula that pretty much everybody knows. It's pretty commonplace. V final squared minus v initial squared is equal to 2 times the acceleration times x. and x is just the distance traveled during this segment that you're looking at. So this is a different way to look at the problem. We know that if we graph out the motion on a velocity by time graph, the total distance traveled is going to be the area under the curve, right? Basically, as you can see in this graph, it's going to be the area of that trapezoid right there. And how do we know what the area of this trapezoid is? We resort to our elementary area formulas, right? Trapezoid is the average of the two bases times height. So b1 plus b2 over 2, and then times the total height of the trapezoid. Well, here, since we're looking at a sideways trapezoid almost, the height's actually going to be the horizontal line, right? From 0 to time final. The two bases are going to be v initial and v final, right? That's the length of those two sides. And so if we want to calculate the area, we have to find out what these values are. Well, the average of the two bases is simple. It's going to be v initial plus v final over 2, right? For the height, however, we know that it's t final minus 0, as we can see on the graph. But what can we do with this time? Because we know the final formula, it's not going to have time in it. So we need to find a way to represent time in a different manner. In essence, we go back to our elementary formula, which is v final is equal to at plus v initial, right? If we rearrange the terms on that equation, we're going to get the t final is equal to the v final minus v initial over the acceleration, as you can see on the slide here. So we're going to take that very convenient value, we're going to plug it back into our original equation, and if we multiply the terms together and we expand that out, right, we know a plus b times a minus b is simply difference of squares. It's going to be v final squared minus v initial squared at the top. The bottom is just going to be 2 times a, so 2 times acceleration. And that's all equal to x, right? X is the distance traveled, the area of the trapezoid. So now what do we do? To get to that formula, all we have to do is simply multiply both sides by 2a, right? Once we do that, we get 2ax is equal to v final squared minus v initial squared, and there we have it. So formula proven, and this is with a different way, different means of looking at it through a case of geometry. So now say that we want to calculate the maximum height of a projectile launched at an initial velocity of v at an angle theta to the horizontal. Well, first, as we've seen on the second slide, we always want to decompose this type of motion into its horizontal and vertical components, unless we know some easy shortcut that's going to take us to the answer really quickly. There's no easy way without splitting it into x direction, y direction motion. Now, since we're looking at maximum height, right, we kind of know that whatever happens along the x direction doesn't change anything. It doesn't, because we can separate it into horizontal and vertical, and whatever happens in the vertical stays vertically. The maximum height now is only going to be relevant to the vertical frame. So we only have to look at that. And now that we've gone past that, we have to analyze what happens at the beginning and end. So at the beginning, we know it's launched with some initial velocity, right? We don't know what it is right now. All we know is that it's launched with velocity v along that angle. But that angle is not exactly vertical. So we have to do something to it to find its vertical component, aka vector decomposition, which we looked at earlier, but we are going to have to tackle here again. Anyways, at the point where its height is maximum, we know that it's about to change direction, right? That means that its speed is going to be at 0. So all the way from the bottom to the top, it's going to start off at velocity, some velocity, again, we'll find that out in just a few seconds, but it starts off at that velocity and it ends at 0. And we're trying to find the distance traveled during that time in the vertical frame, right? That's going to be the maximum height. So we know that by vector decomposition, this vertical vector, this mystery vector that we originally claimed to have not known, is actually going to be v sine theta, right? Horizontally, it's going to be v cosine theta, and you can work this out by right triangle trigonometry. So we have the vertical velocity of v sine theta. And we know that at the very top, its velocity is going to be 0. Right. So we can use that formula that we just derived earlier, v final squared minus v initial squared is equal to 2 times acceleration times distance. And we know initial velocity is going to be that v sine theta, right? Final velocity is going to be 0. And remember, with our equations, always take into account the direction. So since gravity is pointing the other direction, the right side is going to be negative 2gf. So on the left side, we now have negative v sine squared theta, v squared sine squared theta, is equal to negative 2gx. So we have that formula, then we can simply just multiply both sides by negative 1, right? Cancel out that negative. And now we have v squared sine theta squared is equal to 2gx. Okay, well at this point, all we need to do really is to divide both sides by 2g, and we end up getting the total distance vertically traveled, aka now we know it's going to be the maximum height is going to be the v squared sine theta squared over 2g. That's how we can find, in a matter of minutes, the maximum height of this projectile.